Given a linear map L from V to W, it is natural to consider the following two sets. The first of these is called range, and recall that it's a concept we have encountered before. Range can be defined for any function, and it is defined as the set of all images. Therefore, range of L is the set of all L of V where V belongs to capital V. Notice that as L of V belongs to W, this is a subset of W. We are also somewhat familiar with the importance of range. When the range is equal to the codomain, then we give a special name for such functions. Such functions are called surjective functions or onto functions. Now, what makes it even more interesting in this case is that range of L has a linear structure. In other words, range of L is a subspace of W. And that makes it even more interesting. The next set of interest is not something that can be made sense of for a function between two sets. It inherently uses the extra structure that is there in a vector space. Recall that the zero vector is very special. Therefore, it makes sense to look at all vectors in V that are mapped to the zero vector in W. This set is called the null space. For simplicity, we will denote it as null of L. Once again, we will prove that this is a vector subspace of V. Even though null space cannot be defined for functions between sets, you might have seen something that is very similar to null space when you studied groups. Recall that even in groups, there is a special element, namely the identity element. And we can consider all elements in the domain that gets mapped to the identity element in the codomain. And that set was special in group theory. This was called the kernel in group theory. Notice that the kernel and the null space are very similar to each other. Let us now look at the proof that the range and null space are indeed vector spaces, and then we will look at some examples. First, we will show that range is a subspace of W. It is clear that range is a subset of W. Therefore, to show it's a subspace, we have to show three things. We have to show it's closed under vector addition, closed under scalar multiplication, and it contains the zero vector. Let us prove these one after the other. First, we have to show that it is closed under vector addition. Take two arbitrary vectors W1 and W2 in range of L. As they belong to the range of L, there exists V1 and V2 in V such that W1 is equal to L of V1 and W2 is equal to L of V2. But then W1 plus W2 is equal to L of V1 plus L of V2. But linearity implies that L of V1 plus L of V2 is equal to L of V1 plus V2. As W1 plus W2 is equal to L of V1 plus V2, we know that W1 plus W2 belongs to range of L. And thus we have proved that this subset is closed under vector addition. Next, we will prove that it's closed under scalar multiplication. To show it's closed under scalar multiplication, once again we take an arbitrary vector in range of L. As it belongs to range of L, there exists some vector V such that W is equal to L of V. To show that this set is closed under scalar multiplication, we have to show that C into W also belongs to the range of L. As W is arbitrary, this would imply that this set is closed under scalar multiplication. But notice that C into W is equal to C into L of V, but linearity implies that C into L of V is equal to L of CV. Therefore, C into W is the image of CV, which implies that CW belongs to range of L. Therefore, the set is also closed under scalar multiplication. Finally, we will show that 0 belongs to range of L. More precisely, we will show that the 0 vector of V will get mapped to the 0 vector of W under the map L if L is linear. Notice that we are denoting the 0 vector of V and the 0 vector of W by the same symbol. But this should not lead to any confusion. How will we show this? How will we show that L of 0 is equal to 0? Notice that we can write the 0 vector of V as the sum V plus minus 1 into V, where V is any non-zero vector in the vector space V. Therefore, L of 0 is equal to L of V plus minus 1 into V. But linearity says that this is equal to L of V plus L of minus 1 into V. Once again, L of minus 1 into V is equal to minus 1 into L of V, which is equal to 0. Further notice that this proof reveals the fact that the inverse of a vector gets mapped to the inverse of the image of that vector. And this will be useful in some situations. Anyway, we have completed all three steps. That means we have proved the set is closed under vector addition, closed under scalar multiplication, and the 0 element is contained inside it. Therefore, this set is a subspace of W. Let us now prove that the null space is a subspace of V. It is once again clear that the null space is a subset of V. Therefore, we have to check only three things. It's closed under vector addition, closed under scalar multiplication, and 0 belongs to this subset. But this time we will start by showing that 0 belongs to the null space. Why? Because we saw just now, and I want to use that memory, that L of 0 is equal to 0. And that implies that 0 belongs to null space. And therefore, we see that 0 is an element of the null space. Let us now prove that null space is closed under vector addition. How do we show that? To show this, we have to take two arbitrary vectors in null space. That means we take V, W in null of L. But as they belong to null of L, we know that L of V is equal to 0 and L of W is also equal to 0. Therefore, L of V plus W is equal to L of V plus L of W by linearity, and L of V is 0 and L of W is equal to 0, and 0 plus 0 is 0. Therefore, we get L of V plus W is equal to 0, which implies that V plus W belongs to null of L. And thus we see that this set is closed under vector addition. All that remains to be shown is that this set is closed under scalar multiplication. To show this, we take an arbitrary vector in null of L and then show that any scalar multiple, say CV, also belongs to null of L. But notice that as V belongs to null of L, we know L of V is equal to 0. And to show CV belongs to null of L, what we need to show is that L of CV is equal to 0. But by linearity, L of CV is equal to C times L of V. But L of V is equal to 0, so we get C into 0, which is the 0 vector itself. And therefore, we know that CV also belongs to null of L. And this completes the proof that null of L is a subspace. Now notice that we had understood the importance of range and it's directly related with surjectivity. However, it is not so clear to us what is the importance of null of L. But notice one thing, if at all a function L is injective, then the null of L has to be the singleton set 0. Why? Because if it is not the singleton set 0, if there is any other vector V in null of L, then L of V is equal to 0 for that vector V also. And if this V is non-zero, then there are two different elements V and 0 that both get mapped to 0. And therefore the function cannot be injected. Thus we have seen that null of L is equal to singleton set 0 if the function is injective. And we will see that even the converse is true. More precisely, we have the following theorem. A linear map L from V to W is injective if and only if the null space is the singleton set 0. Let us first prove the easy implication. That is, if L is injective, then the null space is equal to the singleton set 0. However, in this case, it's easier to prove the contrapositive of this statement. What is the contrapositive of this statement? The contrapositive is the statement null of L is not equal to the singleton set 0 implies that L is not injective. And if we prove this, then we have proved that if L is injective, then null of L is equal to the singleton set 0. How do we prove this? Notice that if null of L is not equal to the singleton set 0, then there exists a vector V which is not equal to 0 that belong to null of L. But as V belongs to null of L, we know that L of V is equal to 0. But V is not equal to 0. So there exists two different L vectors V and 0 such that L of V is equal to L of 0 but V is not equal to 0, which implies that L is not injective. And that completes the proof of the contrapositive. Therefore, we have seen that if L is injective, then null of L is the singleton set 0. Let us now see the proof of the other side. To prove the other side, let us assume that null of L is the singleton set 0, and using this assumption we will prove that L is injective. In other words, we have to show that if L of V1 is equal to L of V2, then V1 is equal to V2. That's what we have to show. So let L of V1 be equal to L of V2. This implies that L of V1 plus minus 1 into L of V2 is equal to 0. But as L is linear, this would imply that L of v1 plus minus 1 into v2 is equal to 0. Therefore, by the definition of null space, v1 plus minus 1 into v2 has to belong to the null space. But the null space contains only one element, the 0 vector. Therefore, v1 plus minus 1 into v2 has to be equal to 0. But that is the same as saying v1 is equal to v2. Why? We can add v2 to both sides of the equation. And then minus 1 into v2 plus v2 will be equal to 0 and we will get v1 is equal to v2. Thus, we have proved that under the assumption null of L is equal to the singleton set 0, L of v1 is equal to L of v2 implies that v1 is equal to v2. In other words, L is injective. Therefore, we have proved that null of L is equal to singleton set 0 implies that L is injective. And this completes the proof. Now we have seen enough theorems. Let us look at some examples and understand this concept, null space and range, a bit better. As the first example, we will look at the function f from R2 to R4 that takes the element x, y to the element 2x, 3y, x plus y, x minus y. Now let us try to understand what is the null space and range of this function f. Notice that null of f is equal to the set of all x, y such that f of x, y is equal to the 0 vector in R4. But the 0 vector in R4 is 0, 0, 0, 0. So null of f is this set. But notice that f of x, y is the element 2x, 3y, x plus y, x minus y. And we are saying that this is equal to 0, 0, 0, 0. But notice that this implies that 2x is equal to 0, 3y is equal to 0, x plus y is equal to 0 and x minus y is equal to 0. But 2x is equal to 0 implies that x is 0 and 3y is equal to 0 implies that y is 0. Therefore, the null space contains only one vector, namely 0, 0. That is, the null space is the singleton set 0. This implies that f is injective. Now let us understand what is the range of f. To understand range of f, we use one of the observations made in the previous video. Namely, the observation that the function is completely determined by its action on a basis. Therefore, we take the standard basis on R2 and look at the action of f on this basis. And it's easy to see that f of 1, 0 is the vector 2, 0, 1, 1 and f of 0, 1 is equal to the vector 0, 3, 1, minus 1. Therefore, range of f would be the span of these two vectors. Namely, it's the span of 2, 0, 1, 1 and 0, 3, 1, minus 1. In this way, we could find the range of f. Notice that in this example, the dimension of range of f is equal to dimension of the domain. And this is no coincidence. We will see later that this is the case whenever f is an injective function. But that's a story for a later day. Let us now look at another example. This time consider the function f from R3 to R2 that takes the element x, y, z to the element x plus y, z. Let us try to find the null space and range of this function. First, we will find the null space. Null space contains all elements x, y, z in R3 such that f of x, y, z is the 0 vector in R2, which is the vector 0, 0. But as before, notice that f of x, y, z is the vector x plus y, z. And we are saying that that is equal to 0, 0. This happens if and only if x plus y is equal to 0 and z is equal to 0. In other words, we can think of it as all elements x, minus x, 0 where x belongs to R. So this is the null space of this function f. Observe that the dimension of the null space is 1 in this case. Why? Because the null space is spanned by one vector 1, minus 1, 0. Also, as the null space is not equal to the singleton set 0, this function is not injective. Now we will find the range of f. As before, we will do this by looking at the image of the standard basis. Notice that 1, 0, 0 gets mapped to 1, 0. Similarly, 0, 1, 0 gets mapped to 1, 0. And finally, f of 0, 0, 1 is the vector 0, 1. Therefore, as range of f is a subspace, range of f is the span of these three vectors. In other words, range of f is the span of 1, 0 and 0, 1. But the span of these two vectors is equal to R2. Therefore, range of f is entire R2. In other words, f is surjective. Also notice that range of f has dimension 2 and we saw that the null space has dimension 1. And 2 plus 1 is equal to the dimension of R3, which is 3. This again is no coincidence, and this will be the story of the next video.